Hello students, welcome to the 43rd lecture of Physical Pharmaceutics 1 BP302T. I am Dr. Sushma Verma, Associate Professor in the Department of Pharmaceutics, Pharmacy Institute, NIT Greater Noida. Till now we have discussed pH Sorensen scale, right, and application of buffers in our first lecture of this unit, and after that we discussed the pH determination. In part 1 we discussed the electrometric determination of pH, right, and in this part 2 of pH determination we will be discussing the colorimetric method of pH determination, right. So, both these methods are used for the determination of pH, right. We have already discussed electrometric method, which is more prevalent for the determination of pH, and this colorimetric method is more of a primitive method, right, but some recent advances have been made in this part of determination. So, we will be taking up them in this lecture also, right. So, as compared to the electrometric determination of pH, this is a quite primitive type of method of estimation for the determination of pH. It is not generally used nowadays, because this pH meter, this electrometric determination of pH is more sensitive, right. So, the digital point after decimal are more accurate in comparison to this colorimetric determination of pH in case of electrometric determination of pH, right. So, this colorimetric determination of pH initially or previously we used to do in a very primitive manner. What we used to do was that we used to have universal indicators. We had universal indicators, right. It was a mixture of 2-3 dyes, right, and that we need not to discuss. It was you all know what is a universal indicator, right. So, it is a mixture of dyes which can act as indicator for any titration, right. So, we have universal indicator. So, what we do, we have got a range of pH solutions from 3 to 11. Right. So, what we have different pH solutions from ranging from 3 to 11, right. So, we have a pH solution of 4, 5, 6, 7, 8, 9, 10 and 11. So, what we will do, we will add this universal indicator to these pH solutions, right. So, to the pH solution of 3 will add this universal indicator. So, it will give a specific color, because the color is pH dependent, right. So, in a different pH the indicator will give a different color. That is why this estimation is known as colorimetric determination, right. So, we have different colors for different pH ranges from 3 to 11, right. And what we will do for finding out the pH of the test solution, we will take the test solution whose pH is to be determined and will also put the universal indicator to it, right. So, after putting the universal indicator to the test solution, we will see the color of the test solution and will try to match it with the range of different pH solutions which are available with us with a mixture of the universal dye, right. हमारे पास यहाँ पर डिफरेंट जो थे पीएच सॉल्यूशंस थे जिसके अंदर की यूनिवर्सल इंडिकेटर एडिड है, ठीक है। टेस्ट सॉल्यूशन में भी हमने यूनिवर्सल इंडिकेटर ऐड किया और उसका जो कलर है विल ट्राई टू मैच इट विद द डिफरेंट रेंज ऑफ पीएच सॉल्यूशंस दैट वी हैव, ठीक है। तो वो जिसके साथ मैच कर जाएगा दैट विल बी द रेंज ऑफ द पीएच सॉल्यूशन ऑफ द टेस्ट। सपोज 5 आया, ठीक है। So, 5 आया तो we'll assume that our test solution is having a pH range of 5. What we'll do further is we will prepare test solutions of different pH from a range of 4 to 6 within a gap of 0.2 units, right. तो हमको जब एक आइडिया लग गया कि उस पर्टिकुलर सोल्यूशन का कितना पीएच है, तब हम उस पर्टिकुलर रेंज को माइन्यूट पार्ट्स के पीएच सॉल्यूशंस में डिस्ट्रीब्यूट कर देंगे, right. So, we will make different pH solutions within a range of 4 to 6 within a gap of 0.2 units, right. Next we will try to match, right, we have different pH solution, we will again follow the same procedure, we will add the universal indicator to it, and we have already the test solution with the universal indicator. So, we will try to match the solution of the test solution with which pH solution it is matching, right. So, it the color is matched by eye only, right. So, that is why it is a primitive method, right. So, typical colorimetric pH determinations are limited to the pH range of pKa 1.5 units by color transition of the indicator. Previously it was done like that only, right. And so, the pH was analyzed with the eye, and pH of 1 to 7 was determined, right. But now we have some more better methods in this area also, in colorimetric determination of pH also. What we have, like we have the spectrophotometer, UV spectrophotometer in our labs for the determination of the different concentration, unknown concentration, right. Similarly, we have instruments that can tell you the pH of the solutions by the different concentration of the dyes, right. This is the one evolved method of the colorimetric determination. Previously, it was done by the eye. Determination of the color was done by the eye, which finally told you about the pH of the solution, but now it is done colorimetrically, and it is achieved for a diverse variety of samples, right. It is a better method, and it is a more sensitive method as compared to the previous method, right, colorimetric methods, right. Similarly, in the same way like the spectrophotometer, the principle and the procedure are the same as we have in the spectrophotometer. What we have here, that a particular dye will have a specific relative absorbance, right. In a particular dye in a specific pH will have a particular absorbance. This is the characteristics of the particular dye. This is the main thing that we use for the determination of the pH, right. And in this range you find that the relation is a straight line curve, right. As the pH is increased, the absorbance will increase automatically. So, a straight line curve is there, and a association between the two properties is also there, right. So, this is a small range, right. We can use a mixture of dyes also for this determination. So, this graph 1, right, this is a single dye, this is the curve for the single dye, right. You see here that it is a small range, right, it is a for the single dye, and if you want to enlarge the range, you can use a mixture of dye, right. And in the curve B, you can see that the range of the dye, mixture of dye is increased as compared to a single dye, right. So, the theory behind the principle of colorimetric determination is that absorbance versus pH for a given dye will be approximately linear over the range, right. So, this relationship, that is pH versus absorbance. So, as the pH of the solution increases, so the absorbance will increase. So, this linear relationship should be through quite a range, right. It should be elaborated over a range of pKa plus minus 1.0. The exact relationship between concentration of absorber is given by the Henderson-Hasselbalch equation, right. And this equation shows that pH is equal to pKa plus log of salt upon acid, right, where salt and acid denote the concentrations of the dye in the salt and acid form having the specified pKa, right. What we have? We have a dye, right, and it has two forms, one is the salt form and another one is the acid form, and pKa is the specific property of the dye, right. So, pH can be indicated by the dye if we have the concentration of the dye in the salt and in the acid form, right. If we have these two parameters, this is a constant, right. If we can get these two values, then pH can be determined, right. So, this is the theory behind the conductometric determination of pH. One of the dye forms, either salt or acid, is the absorber measured colorimetrically, right. Either the salt form or the acid form, it will absorb a specific wavelength of light in correspondence to the pH of the solution, right. So, it will absorb light at a specific lambda max, right, like we have different powder or different substances, they are absorbing light at different wavelengths. In the same way, we have dye, it is in the salt form and it is also can be it on the acid form, and it absorbs light at a specific wavelength, and the equation is solved by using a fixed concentration of dye, right. What we have kept constant here is the concentration of the dye, Ct, according to it Ct is equal to acid plus salt, right. The concentration of dye is represented by Ct, and it is a combination of the dye either in the acid form or in the salt form. For a dye mixture where the two dyes have the same salt and acid spectrum, that is approximately the same, right. So, for a mixture you can select the dyes which are having approximately the same wavelengths, right, of maximum absorption, right, because this is the particular characteristics which is used for the determination, right. They should have same wavelength, only then they will be able to absorb in that particular range, right, and same molar absorptivity, right. This is the second requirement, they should have the same molar absorptivity ratio at the two wavelengths, slightly different pKs, right. And because two compounds cannot have all the characteristics same, so there is a relaxation that is given. So, they can have slightly different pKas, right, and that can be referring to 1.6 pH units, right. Then the linear curve can be extended by appropriate combinations of the dye, right. If we have this type of a setup, this type of a mixture, we have a mixture of dye which are having the same wavelengths of maximum absorbance and same molar absorptivity, right. So, we can use them, and the only thing that is relaxed is that they can have different pKs, and they can have the difference of pKs can range from 1.6 pH units, right. So, we will get a linear curve like we have seen in the diagram previously. The P curve was given by the mixture of the dyes, two dyes, right, that can be in the acid or the salt form, and that can be used for the estimation, right. If we want to make a wide pH range dye mixture, right, for that a 4 component dye mixture is recommended, and you have to accurately weigh 25.4 milligram neutral red, this is the dye, 10.2 milligram methyl red, 7.8 milligrams methyl yellow, and 14.1 milligram thymol blue into a 500 ml volumetric flask, and it is diluted with methanol, right. And we use these 4 dye in a mixture in a 500 ml volumetric flask with methanol, and which is diluted to 50 ml with distilled water. So, this is the composition of the dye, which is a 4 component wide range dye which can be used for the determination of different compounds, different test solution, they can determine the pH of a wide range of test solutions, right. Next is the general directions for dye preparation. So, how will you prepare the dye? So, you have the 4 components. So, how will you prepare the dye? It is the same procedure that you follow for making the stock solutions of the drug whose spectrophotometrically UV evaluation you have to carry out, right. So, stock solutions of individual dyes 50 milligrams per 100 ml should be prepared, right, and undissolved dye should be removed by filtration or using a filter paper, and small allocates of this 10 to 100 microliters depending on dye concentration of each stock solutions are diluted to 10 ml of 1 molar HCl, and the absorbance is read at 565 nanometer on a spectrophotometer, ठीक है। तो हमने क्या किया, स्टॉक सोल्यूशन बनाए डाइस के, ठीक है, वाइड रेंज वाले के इन अ कंसंट्रेशन ऑफ 50 मिलीग्राम्स पर 100 ml, एंड फ्रॉम दैट allocates small samples of 10 to 100 microliters were taken from each stock solution and they were diluted to 100 ml, ठीक है। तो एक 100 ml solution हमने बना लिया सब डाइज का with 1 molar HCl, and we have taken up the absorbance at 565 nanometers spectrophotometrically. The dyes are blended such that each dye will contribute to the same absorbance, ठीक है। तो डाई की कंसंट्रेशन हमको इस तरह से चूज करनी है कि फाइनली जो है एब्जॉर्बेंस सेम लैम्डा मैक्स पे आए, राइट। It will the selection of the dyes or the blend of the dye should be such that each dye will contribute the same absorbance to the final solution when in the acid form. For example, if dye A reads 0.2 absorbance unit per microliters diluted to 100 ml and dye B reads 0.1 absorbance unit per 50 microliters diluted to 10 ml, then 1 unit of absorbance from dye A would require 0.05 ml, है ना, क्योंकि different concentration में उनकी different absorbance है, क्योंकि different dyes हैं, right. So, we have to take that concentration of that particular dye which will contribute to the same absorbance, ठीक है। दोनों dyes की concentration इस तरह से select करनी है कि उनकी जो absorbance आए वो same हो, राइट। सो अगर एक की वो ज़्यादा कंसनट्रेटेड फॉर्म में वो एब्जॉर्बेंस देते, एक को तो डाइल्यूट में है, तो उनका जो है डेफिनेट प्रोपोर्शन आपको सिलेक्ट करना पड़ेगा सो दैट वी कैन गेट द सेम एब्जॉर्बेंस ऑफ द फाइनल सोल्यूशन व्हेन द एसिड फॉर्म इज देयर, राइट। So, A would require 0.05 ml and 1 unit of absorbance from dye B would require 0.5 ml. Therefore, the correct dye mixture ratio is 10 parts dye B per 1 part of dye A, right. So, we will select the concentration of the dyes in such a manner so that they will contribute to the same absorbance together. The ratio of the dye to sample should be adjusted such that the absorbance at 555 nanometers of the sample plus dye will be approximately 1 when the resulting solution is 1 molar in hydrogen ion solution, ठीक है। और इसी तरह से आप जो है डाई टू सैंपल जो रेशो है वो इस तरह से एडजस्ट करेंगे कि 555 नैनोमीटर्स पर जो आपकी एब्जॉर्बेंस है वो 1 आए, राइट, in 1 molar hydrogen ion solution. Next is the sample selection and preparation. Prepare buffer that will resist change in pH upon modest dilution for use as standards. These buffers should be adjusted in the correct pH by addition of dilute HCl or NaH, ठीक है। बफर सॉल्यूशंस बनाएंगे और उनका pH फिक्स कर देंगे by using HCl और NaH, है ना, versus करेक्ट वैल्यू वर्सेस अ कैलिब्रेटेड पीएच मीटर, ठीक है। एक कैलिब्रेटेड पीएच मीटर के साथ जो है बफर सॉल्यूशंस बनाएंगे, राइट। 9 बफर्स spanning from the range of 1 to 9 having values spaced 1 pH unit apart are necessary, right. जैसे initially I have told you in the previous primitive method that we have different pH solutions or different buffer solutions of range 3 to 11, right. So, similarly, we will also here make buffer solutions of different pH range within 1 to 9 having values spaced 1 pH unit apart are necessary. Suitable commercially available colorless buffer solutions are available and tablets are available. You can directly take the tablet and make the solutions. Colorless clear samples work best and require no blank corrections. However, accurate results can be obtained on turbid or faintly colored samples when diluted or blank corrected. For clear or colorless liquid samples, the buffer standards mix 2 ml of unknown with 8 ml of aqueous dye, right. You have to mix buffer solution and 8 ml of dye. For colored and turbid samples, for example, lemon juice, mix 2 ml of sample with 8 ml of water, right. इसमें अगर आपके पास turbid solution है या colored है तो जो composition है वो different हो जाएगी buffer के साथ, right. 8 ml of water for use as blank or alternatively the samples may be diluted with water prior to use. Solids can be dissolved in 10 ml of water or alcohol for organic solids, for example, aspirin followed by filtration through fast filter paper and 2 ml of the solution can be used as a sample. So, this was the sample preparation कि कैसे select करेंगे कि आपने different range के buffer solutions बनाए और आपके पास फिर test solutions है उसको different dye के साथ different composition में mix करके आप different pH के solutions बनाएंगे. The samples can be compared visually to the buffer standards and an estimate of the pH to approximately 0.5 units can be performed directly, right. तो जो samples हैं आप उसको visually eye से भी जो है compare कर सकते हैं approximately to the range of 0.5 pH unit can be performed. The visual comparison works best if solutions are prepared in 18 into 150 mm test tubes. Alternatively, the absorbance can be read on a spectrophotometer. So, this is the elaborate version of this technique. So, initially it was done, the color comparison was done by eye, now it has been done by a spectrophotometer, right. The same way in which we are analyzing the standard curves or we are analyzing the different unknown concentration and we are getting different absorbance and we are making standard curves. Similarly, we have got a curve here also that is versus pH and absorbance, right. At different pH we have different absorbance of the indicators, right. In a 1 centimeter glass cell, a Beer's law plot is constructed for the standards and the pH of the unknown using blank corrected absorbance where necessary is directly from the calibration curve, right. So, in the same way we can have a curve, we have pH here and we have absorbance here. So, we used to have buffers of 1 to 9 range, right. We have 9 buffer solutions. So, we can write here if pH is 1 then what will be the absorbance here. So, we can plot this curve here, right. We can plot a point here. So, at pH 2 what will be the absorbance. So, it is following a Beer's law. So, it will be a straight line curve, right. So, at pH 3 the absorbance is here, pH 4 absorbance is there. So, if we make a line out of these points we will get a straight line, right. So, this is for the buffer solutions whose pH we are knowing, right. This is the pH we are knowing and this is the absorbance for the known pH solutions, known pH buffer solutions. And if we have got an unknown solution, what we can do is we can take that solution, we can add the dye to it and we can get the absorbance for that particular solution and that absorbance can be extrapolated, right. Suppose the absorbance for the unknown solution we get here, right. So, this can be extrapolated from this graph to this point, right, and we can get the pH of the unknown solution. In the same way that we can get the concentration of the unknown solution in the dissolution test apparatus system using a UV spectrophotometer, right. So, it is the same way that we are getting. And for this topic, you can refer a different book that is written by Skoog and West and Holler. These are the fundamentals of analytical chemistry, 5th edition. Saunders is the publisher and published in New York, and you can follow the page number 182 to 184. You find the colorimetric method is given in detail. So, you will not find this method in physical pharmacy by Martin, right. So, this method is specifically given in this book, Skoog and West and Holler, right. This is a book of basically analytical chemistry, right. So, these are the actually determination methods of the pH. So, it is taken up in the analytical chemistry book. So, you can find this topic in a elaborative manner in the book, right. And to a little extent, only briefly it is described in CVS Subramaniam, and I am not able to find this topic in any of the books, right. This is only in this Skoog and West, and you can search articles if you want. Some articles are also there on this method. So, which earlier was a very primitive method, right. This is almost an obsolete method which has been revived due to the addition of the determination of the pH by spectrophotometer, right. Earlier it was done by eyes, visualization done by the eyes, but now it is done by the spectrophotometer. So, this technique has gained new success, right, since the addition of this spectrophotometer. Now, it is also a determinations method of choice due to the addition of this spectrophotometers, right, and these are the references. You can follow this book. Thank you so much, right. That was all regarding the conductometric determination of pH. So, till now we have covered the general introduction of pH, its pH scale, application of buffers and pH determination. In part 1 it was the electrometric determination of pH, and in this part we have carried out the conductometric determination of pH. So, this completes our determination of pH by both the methods, electrometric and conductometric. Thank you so much.